Namaste. My name is Partha Majumdar. I am pursuing Masters in Indian Knowledge System from Bhishma School of Indic Studies. My PRN is 23110779. This is my submission towards the project for semester 2. My topic is the profundity of Vedic knowledge in understanding the universe's origin. The quest to understand the universe's origin has captivated human thoughts across cultures and centuries. In the modern scientific era, two primary theories have gained prominence: the Big Bang theory and the steady state theory. These theories, which emerged in the 20th century, offer scientific explanation of the universe's beginning and the current structure. The Big Bang theory posits that the universe began from a singularity approximately 13.8 billion years ago and has been expanding ever since. On the other hand, the steady state theory suggests that the universe has always existed constantly, with the continuous creation of matter ensuring its uniformity over time. However, long before these scientific paradigms, the ancient Vedic texts, particularly the Rigveda, provided cosmological perspectives that have endured for millennia. The Rigvedic theory of creation, expressed through hymns like the Nasadiya Sukta, offers profound metaphysical understanding of the universe's origin. While these ancient ideas are often seen as spiritual or symbolic, they present concepts that resonate with the modern scientific theories in surprising ways. Notably, the Vedic version of cyclical creation and dissolution and the role of abstract cosmic principles offer insights that may anticipate or complement scientific views. This study will explore the profound connection between the Vedic cosmology and modern scientific theories, positioning Vedic knowledge as a framework that offers rich, scientifically relevant insights into the universe's origin. Through a comparative analysis of Big Bang theory, steady state theory, and the Rigvedic theories, this research aims to demonstrate that Vedic cosmology was far ahead of its time, providing sophisticated understanding of the cosmos that modern science is only now beginning to catch up with. I will now lay out the mechanics of this study. The study hypothesizes that Rigvedic theory of creation is philosophically rich and offers scientific value. The Vedic cosmology, often dismissed as mythology or mystical, contains concepts that align with or even predate the fundamental principles of modern scientific theories about the universe's origin. The Rigveda's metaphysical approach to universe's origin, with its cyclical notion of time and creation, anticipates the fundamental questions modern science has grappled with for over a century. I hypothesize that modern theories like Big Bang theory and steady state theory are subsets of the broader, more profound cosmological understanding embedded in the Vedic texts. The research aims to establish intellectual depth of Rigvedic cosmology and its relevance to modern cosmological theories. Second, compare the fundamental principles between the Big Bang, steady state, and the Rigvedic theories, focusing on the origin and evolution of the universe. Now, thirdly, it provides evidence that modern scientific cosmology is beginning to catch up with the profound insights of the Vedic text, especially regarding the cyclic nature of creation and destruction, the concept of infinite expansion, and the role of consciousness in the universe. The scope of the study will focus on three key areas: the Big Bang theory, the idea that the universe originated from a singularity around 13.8 billion years ago, followed by rapid expansion. Also, we will touch upon the steady state theory, that the concept that the universe has always existed, and in a constant state without beginning or end, with continuous creation of matter. Lastly, we will discuss in detail the Rigvedic theory, the cosmological ideas in Rigveda, particularly the cyclic view of creation and destruction, that is Pralaya, and the emphasis on the unknowable abstract cosmic principle, that is Brahman. The study's limitations include the difficulty of directly correlating metaphysical and symbolic Vedic description with empirical scientific data. Additionally, some of the interpretations of the Vedic text are subject to scholarly debates. The study will employ a multidisciplinary approach, incorporating a textual analysis of the Rigveda and the scientific views of cosmological theories. The research will be conducted in three phases. In the first phase, we will conduct a comprehensive literature review examining the primary and secondary literature on Big Bang theory, the steady state theory, and the Rigvedic cosmology. These will include scientific papers, books, and commentaries by physicists and Vedic scholars. In the second stage, we will do a comparison of the cosmological concepts within each theory, focusing on their explanation for the universe's origin, structure, and fate. This analysis and this will analyze common themes like creation from nothingness, expansion, and cyclicity. Lastly, using a comparative study to demonstrate how Rigvedic cosmology offers a more profound and encompassing view of the universe's origin than is recognized in the modern scientific discourses. This will also highlight areas where modern science converges with the Vedic thoughts, particularly in the concept of cosmic cycles and the nature of time and space. The research is significant for both scientific and philosophical reasons. By bridging ancient Vedic wisdom with contemporary cosmology, the study will shed light on the potential for cross-cultural intellectual exchange and the value of ancient knowledge system in advancing modern scientific thoughts. It will also highlight the broader philosophical implication of cosmological theories, how our understanding of the universe affects our sense of existence, purpose, and the divine. The study can offer new perspective on the nature of reality, time, and the cosmos, encouraging more integrated approach to science and spirituality. The expected outcomes of the studies are as follows. 1. To demonstrate the intellectual depth of Rigvedic cosmology and its alignment with modern cosmological concepts. Second, to challenge the assumption that Rigvedic knowledge is purely spiritual and mythical by presenting it as a sophisticated cosmological framework. Lastly, to encourage further interdisciplinary research between ancient philosophies and modern sciences. The project will explore how, far from being outmoded, the Rigvedic concept of universe's origin offers profound insights that complement and even enhance modern scientific theories. By re-examining the wisdom of the Vedas, we can deepen our understanding of the cosmos and our place within it. The first step in the study is the literature review. The literature review explores the significant contributions from various scholarly works on the Big Bang theory, steady state theory, and the Rigvedic cosmology, aiming to comprehensively understand how modern cosmological theory compare with Vedic knowledge. The review will examine the scientific and philosophical dimensions of universe's origin, considering how Vedic cosmology anticipates modern theories and where these theories diverge. Let us start our discussion with the Big Bang theory. Stephen Hawking's book, A Brief History of Time, is one of the most popular and influential books explaining the Big Bang theory. Hawking addresses the fundamental principles of cosmology in an accessible manner, covering topics such as space-time singularity, black holes, and cosmic inflation. His collaboration with Roger Penrose further advanced the theoretical understanding of gravitational singularities, asserting that the Big Bang was a product of the laws of general relativity, which govern large-scale cosmic structures. The theory of cosmic inflation, proposed by physicist Alan Guth in the early 1980s, provided a solution to some of the Big Bang's unresolved issues, such as the horizon and flatness problem. Guth's work, elaborated in his book, The Inflationary Universe, explains how the universe expanded exponentially in the first fraction of a second, leading to a large-scale uniformity observed in the cosmic microwave background. The discovery of CMBs, or cosmic microwave background, by Arno Penzias and Robert Wilson in 1964 provided substantial evidence supporting the Big Bang model, as it represents the remnant radiation from early universe shortly after the Big Bang. In collaboration with Robert Penrose, Hawkins further explores the intersection of quantum mechanics and general relativity, particularly in their work on the Penrose-Hawkins singularity theorems. These theorems argue that the universe's beginning, as described by the Big Bang, is a point where both time and space break down, leading to a singularity where the known laws of physics cease to apply. Hawkins' book, The Nature of Space and Time, co-authored with Penrose, delves deeper into these topics, explaining the interplay between quantum mechanics and cosmology. Modern cosmology owes much of its current understanding of the Big Bang to advances in observational astronomy. Edwin Hubble's discovery of the redshift of galaxies laid the groundwork for the theory. The correlation between a galaxy's redshift and its distance from Earth suggests that galaxies are receding from us, consistent with the expanding universe. The concept is known as Hubble's law and was further explored by theorists such as George Gamow, who also contributed to understanding nucleosynthesis, a process by which elements are formed in the universe's early moments. The Large Hadron Collider (LHC), operated by CERN, provides additional insights into the conditions that existed just after the Big Bang. By recreating high energy conditions akin to those in the early universe, the LHC experiment allows scientists to study particles' interactions and energy states that help explain the forces shaping the cosmos. The discovery of Higgs bosons in 2012 confirmed the existence of Higgs field, a critical component of the standard model of particle physics, which plays a role in understanding how particles acquire mass. Additional support from the Big Bang comes from large-scale observational projects such as Wilkinson Microwave Anisotropy Probe (WMAP) and the Planck satellite. These projects have mapped the CMB in extraordinary detail, allowing cosmologists to accurately estimate the universe's age, composition, and geometry. These studies have revealed that the universe is flat and composed of about 4.9% ordinary matter, 26.8% dark matter, and 63.8% dark energy. While the Big Bang theory provides the most comprehensive model of universe's origin, it leaves several questions needed to be solved. Let us explore these avenues. The first question is, the genesis of the singularity is not explained. The Big Bang theory begins with the concept of a singularity, a point of infinite density and temperature from which the universe is believed to have expanded. However, the theory does not explain the origin of this singularity or what caused it to exist. The singularity remains a profound mystery as it represents a state where the known laws of physics, including general relativity, breaks down. This beginning of everything leaves scientists and philosophers with unanswered questions about the nature of time, space, and existence before the Big Bang. Despite significant advances in cosmology, no universally accepted theory currently explains the creation of the singularity or what triggered the universe's rapid expansion. Various hypotheses attempt to address this issue, such as quantum fluctuation or high-dimensional physics, as proposed in the string theory and the multiverse hypothesis. Still, they have yet to be definitely proven. The failure to explain the genesis of the singularity leaves critical gap in our understanding of cosmology, pushing the boundaries of science into the realm of speculative physics and metaphysical inquiry. The second objection to Big Bang theory comes from the failure of Newtonian physics to explain the Big Bang theory. Isaac Newton's classical mechanics provided the foundation for understanding the universe for centuries, primarily through his laws of motion and the universal gravitation. However, Newtonian physics could not adequately explain the Big Bang theory for several reasons. First, the absence of relativistic effects. Newtonian framework assumes that the time and space are absolute, which contradicts the relativistic nature of the Big Bang, where space-time is dynamic and evolves. The second failure is the inability to address extreme conditions. Newtonian physics fails to describe the conditions in the early universe with extreme densities and temperatures. The Big Bang involves the behavior of matter under such extreme conditions, and Newtonian mechanics breaks down in these scenarios. The third failure of Newtonian physics is the cosmological model itself. Newton's theory does not include a cosmological constant essential for explaining the expansion and the contraction of universe. The Newtonian model assumes a static universe, whereas the Big Bang theory posits an evolving cosmos that changes over time. Because Newtonian physics treats gravity as a force that acts instantly across space, it also does not account for finite speed of light, which is crucial in understanding the propagation of gravitational effect over cosmic distances. While Newtonian framework was effective for explaining planetary motions and other phenomena within the solar system, it is inadequate to address the universe's complexities on cosmic scale. The Einstein's relativity theory overcame the limitations of the Newtonian theories. The Einstein's theory of general relativity introduced in 1915 overcame several uh, concepts which in support which supported the Big Bang theory, particularly the dynamics of space-time and gravity. Relativity replaced the Newtonian concept of gravity as a force acting at a distance with an idea that gravity is a curvature of space-time caused by mass and energy. This was crucial in explaining the cosmological phenomena like the Big Bang. Einstein's general relativity showed that space and time are not absolute, as Newton believed, but are interwoven into a four-dimensional space-time fabric that can stretch and curve. This dynamic view of the universe was essential for explaining how space-time could expand as the Big Bang theory required. Relativity applies even in extreme conditions such as those near black holes or at the universe's beginning when density and temperatures were extraordinarily high. Einstein's equation can describe these high energy environments more accurately than Newtonian physics ever could. General relativity predicted that the universe could expand or contract, a prediction confirmed by Edwin Hubble's observations of receding galaxies in 1920. Einstein's equation laid the groundwork for model of expanding universe, a cornerstone of the Big Bang theory. However, even general relativity has limitations, particularly when reconciling the gravity with quantum mechanics. The theory breaks down at singularity and quantum effects, which are not accounted for in general relativity, are believed to play a significant role in developing the early universe. Many modern discoveries support the Big Bang theory, though they are also highlighted areas where our understanding remains incomplete. The discovery of type La supernova, which acts as a standard candle for measuring cosmic distances, provided key evidence for the universe's accelerating expansion. In 1998, the observation that distant supernovae were fainter than expected suggested that the universe's expansion was continuing and accelerating. This discovery led to the postulation of dark energy, a mysterious force driving the acceleration. However, when supernova observations support the Big Bang model, they also raise questions about the nature of dark energy, which remains one of the biggest unknowns in the cosmological sciences. Black holes are objects with intense gravitational field that no light can escape. These existence support the prediction of general relativity and, by extension, the conditions thought to exist shortly after the Big Bang. However, black holes also highlight the conflict between general relativity and quantum mechanics. The mathematics describing the black holes predicted singularities, much like the singularity at the beginning of the Big Bang, where densities became infinite and the laws of physics as we know them break down. This suggests that a quantum theory of gravity is needed to understand these phenomena fully. Discovered in 1964 by Arno Penzias and Robert Wilson, the cosmic microwave background CMBs provide a snapshot of the universe when it was just 380,000 years old. The faint glow of radiation, a relic from early universe, has been measured with increasing precision by projects like COBE, WMAP, and Planck. The uniformity and slight variations in the CMB provide critical evidence for the Big Bang, supporting the idea of an early, hot, dense universe. However, anomalies in the CMB, such as the cold spot, are not yet fully explained by current models. Despite its success, the Big Bang theory must account for the nature of dark matter and dark energy, which comprise about 95% of the universe's mass energy content. Dark matter, which interacts gravitationally but not electromagnetically, is thought to hold the galaxies together, while dark energy drives the universe's accelerated expansion. Neither of these concepts and components is explained by the Big Bang theory or the current models of particle physics. Now let us discuss the steady state theory. The steady state theory was developed in the mid 20th century as an alternative to the Big Bang theory. Pioneered by British astronomers Herman Bondi, Thomas Gold, and Fred Hoyle, this theory proposes that the universe is eternal and unchanging on a large scale. This theory suggests that the universe has no beginning or end. Unlike the Big Bang theory, which posits a singular moment of creation. In steady state theory, the matter is constantly created to maintain constant density as the universe expands. The ongoing creation of matter balances the universe's expansion, ensuring it remains steady. The steady state theory emerged from the philosophical debate in the mid 20th century about the nature of universe and its existence over time. One of the central principles, the perfect cosmological principle, posits that the universe should appear uniform and consistent in all directions, that is isotropy, and remain unchanged over time, that is homogeneity. The concept was a significant departure from other models such as the Big Bang theory, which suggested that universe's appearance and conditions evolved. In the steady state theory, the universe is eternal, with no beginning or end. It is continuously replenishing itself with newly created matter to maintain constant density despite the observable expansion of space. Fred Hoyle, along with Hermann Bondi and Thomas, was proposed a theory whose motivation was deeply philosophical, driven by the desire to avoid models that implied moment of creation as the Big Bang theory did. Hoyle and his colleague found the idea of a universe with specific origin troubling because it seemed to necessitate an act of creation, which they felt introduced unnecessary theological implications into the cosmological discussion. By proposing continuous matter creation, Hoyle established a model that could account for the observable expansion of the universe without involving a single creation event. In his seminal work, The Nature of Universe, Hoyle elaborated on the theoretical framework, laying out how the steady-state theory differed from the Big Bang. His preference for eternal, unchanging universe reflected a scientific and philosophical inclination to avoid models suggesting a temporarily bound event like the beginning or the end. By advocating for steady-state model, Hoyle and his contemporaries sought to present a universe that was always in equilibrium, one that perpetually created new matter in existing regions of space to counterbalance the dispersal of existing galaxies. The philosophical resistance to a singular beginning was rooted in a broader desire among some of the scientists and thinkers to avoid cosmological models that may parallel or imply theological ideas, particularly those of creation as described in religious texts. For Hoyle, the perfect cosmological principle provided an elegant solution to these concerns as it supported the idea of eternal universe, a universe without any historical reference point to a specific moment of creation or origin. Thus, the genesis of steady-state theory reflects a blend of scientific observation, mathematical formulation, and philosophical resistance to the notion of an initial moment of creation. Despite its decline in favor following the discovery of cosmic microwave background radiations, that is CMBs, which provided significant evidence for the Big Bang theory, the steady-state theory's origin is a testament to the complexity of cosmological thinking in mid-20th century, where scientific and philosophical considerations were deeply intertwined. Despite its philosophical appeal and early support, the steady-state theory encountered significant challenges in the 1960s, which led to its eventual decline. One of the most critical blows came from the discovery of cosmic microwave background radiations, that is CMBs, in 1965 by Arno Penzias and Robert Wilson. The CMB is considered the thermal afterglow of early universe and serves as compelling evidence for the Big Bang model. The radiation, which is uniform in all directions, is consistent with a universe that began in a hot, dense state and cooled down over time as it expanded. This background radiation directly contradicted the steady-state theory positing an eternal and unchanging universe with no initial hot phase. Before the CMB discovery, the steady-state theory had relied heavily on the idea that the universe looked the same in every direction at every time, and an assumption known as the perfect cosmological principle. However, the observations of distant galaxies which appear younger and less developed at higher redshifts indicate they are observed as they were earlier in cosmic history posed another challenge. These observations showed that universe has changed over time and was not as uniform in the past as the steady state theory required. The finding of younger galaxies at higher redshifts further supported the Big Bang theory, which predicts that the universe has evolved since its origin. Hoyle and his colleagues, including Thomas Gold and Herman Bondi, initially responded to these challenges by attempting to modify the steady state theory. They introduced variations like quasi-status state cosmology, which proposed episodic creation events to explain observed anomalies. However, these modifications needed to account for an accumulating observational evidence favoring the Big Bang model. The CMB remained a hurdle for the steady state framework and could not and as it could not explain this satisfactorily. Further challenges to the steady state theory came from development of the galaxy formation models and the distribution of galaxy clusters. Study in 1970s and 1980s showed that the universe's large-scale structure, including galaxies, clusters, and superclusters, fit well with the predictions of the Big Bang model, accounting for the universe's development over time. In contrast, the steady state theory, which maintained that new matter was constantly created to keep the universe's density constant, could not adequately explain the formation and distribution of these large structures. Despite the overwhelming evidence against the steady state theory, Fred Hoyle remained a vocal critic of the Big Bang theory. He proposed several revisions to the original theory, including the quasi steady state model mentioned earlier, but none gained significant traction in the scientific community. By the late 20th century, the steady state theory had largely fallen out of favor, with Big Bang theory becoming the dominant cosmological model. Now let us discuss Rigvedic cosmology. Rigvedic cosmology offers a profound and metaphorical exploration of the universe's origin, most notably through Nasadiya Sukta, or the hymns of creation in the Rigveda. The hymn discusses the primordial state of the universe characterized by formlessness, chaos, and absence of discernible elements like light, space, or time. Unlike the modern scientific focus on empirical data, Rigvedic cosmology approaches the universe origin through philosophical and spiritual lenses, questioning the unknowable aspects of creation and the nature of reality. In Nasadiya Sukta, the universe is said to have emerged from an undefined state, described metaphorically as a deep void or non-existence, asat, gradually transitioning into existence, or sat. This reflects the idea of creation arising from nothingness, which resonates with the concept of singularity in the Big Bang theory, where the universe is thought to have expanded from a point of infinite density. However, Rigvedic thought does not posit a singular creation event. Instead, it embraces the cyclical cosmology, suggesting that creation and destruction are ongoing, repetitive processes akin to modern cyclical and oscillating universe models. These models in physics, which indicate the universe undergoes cycles of Big Bang and big crunches, mirror the Vedic understanding of cycles of creation, that is Srishti, and dissolution, that is Pralay. Subhash Kak's book, The Astronomical Code of Rigveda, delves into the encoded astronomical knowledge within the Rigveda, arguing that Vedic texts anticipate many modern cosmological discoveries. For instance, Kak highlights the reference to the cosmic order, Rata, which is interpreted as the laws governing the universe's operations, laws modern science seek to explain through physics. Kak also suggests that Vedic seers possessed an intuitive understanding of the cyclical nature of time, a concept that modern physics is only beginning to explore about theories like the multiverse and oscillating universe. David Frawley, in his book The Rigveda and the History of India, presents a holistic analysis of Vedic cosmology, emphasizing the integration of science, philosophy, and spirituality in Vedic worldview. According to Frawley, Vedic cosmology revolves around the concept of Brahman, the ultimate reality, or the cosmic principle that underlies the universe. Brahman is both immanent and transcendent. Through this principle, the universe is thought to manifest and dissolve cyclically. Focus on consciousness in Vedic cosmology also distinguishes it from pure materialistic view of the universe. The Vedic texts suggest that consciousness, rather than being a byproduct of physical universe, is fundamental to its creation and structure. The philosophical emphasis on consciousness aligns with modern debates in cosmology and quantum mechanics, where observers' effect and role of consciousness in shaping reality is increasingly explored. As Trolley points out, Rigvedic cosmology does not separate the physical and spiritual realm. Still, it treats them as interconnected aspects of the same reality, a perspective that enriches the scientific discourse on the universe's origin by incorporating metaphysical dimensions. Now that we have discussed the theories individually, let us do a comparative analysis of the three theories. The three theories of cosmology, the Big Bang theory, the steady state theory, and the Rigvedic point of view, present distinct perspectives on the universe's origin, structure, and faith. This comparative analysis will focus on the key aspects of creation from nothingness, expansion, and the universe's cyclicity, offering insight into how these theories intersect and diverge. First, we discuss creation from nothingness. The idea of creation from nothingness is central to scientific and philosophical cosmology, particularly in addressing the universe's origin. The Big Bang theory provides modern scientific thought's most widely accepted explanation. It suggests that the universe originated approximately 13.8 billion years ago from a singularity, a state of infinite density and temperature. The singularity marks a point where the laws of physics, including time and space, break down as we understand them. The universe rapidly expanded from this singularity, forming galaxies, stars, and all matters. While Big Bang theory offers the model of universe's evolution after this expansion, it leaves unanswered fundamental questions about what caused the singularity or what, if anything, existed before it. The concept of nothingness leading to something remains one of the major philosophical challenges in modern cosmology. By contrast, the steady state theory developed by Bondi, Gould, and Hoyle rejects the notion of singularity. Instead, it proposes the universe is eternal and remains in steady state over time. As the universe expands, new matter is constantly created to maintain its constant density. The theory avoids the idea of creation event from nothingness but fails to explain the mechanism through which new matter is continuously generated. Despite its philosophical appeal, the steady state theory could not account for data observation evidences such as cosmic microwave background radiations, which strongly support the Big Bang theory. The Rigvedic cosmology, as described in the Nasyadhya Sukta of Rigveda, approaches the question of creation from a more metaphysical and philosophical perspective. In this hymn, the universe is said to have emerged from a state of primordial chaos where neither existence, Sat, or non-existence, Asat, was present. The hymn poetically describes a time when there was neither light nor darkness, neither space nor time, raising profound questions about the nature of creation itself. Interestingly, the hymn acknowledges the mystery of creation, noting that even the gods may not fully understand how the universe came into being, leaving the ultimate question of creation open to speculation. This Rigvedic notion aligns with modern inquiries into creation from nothingness, mirroring the philosophical challenge posed by the Big Bang theory's singularity. Both frameworks suggest that the universe emerged from a indefinable primordial state. While modern science seeks empirical evidence to explain this, Rigvedic text reflects a deeper metaphysical inquiry, emphasizing humans' knowledge limit in understanding universe's origin. This acknowledgement of the unknown is Rigvedic cosmology parallel to modern cosmology's uncertainty regarding the origin of singularity and the nature of nothingness. Second, let's discuss the expansion of the universe. The expansion of the universe is a central concept in modern cosmology, particularly within the frameworks of Big Bang theory. Edwin Hubble's groundbreaking discovery of the redshift in distant galaxies in 1929 provided direct observational evidence that the universe is expanding. The redshift phenomena demonstrated that galaxies are moving away from each other, implying that the space between them is increasing. This observation is crucial in supporting the Big Bang theory, as it suggested that the universe began from a dense, hot initial state and has been expanded ever since. Further development in cosmology, particularly in the concept of cosmic inflation, have expanded our understanding of the process. Alan Guth proposed that in the first fraction of the second after the Big Bang, the universe underwent an extremely rapid expansion known as inflation, which smoothed out the irregularities and allowed for formation of large-scale structures we observe today. After this period of rapid inflation, the universe continued to expand at a slower but consistent rate, which is still observable today. The ongoing expansion is measured through the increasing distance between galaxies, reinforcing that the universe is not static but continuously evolving. In contrast, the steady state theory proposed by Hoyle, Gould, and Bondi acknowledges the universe expansion but differs fundamentally from the Big Bang model. Whereas it agrees the galaxies are moving apart, the steady state theory posits that the universe remains the same on a large scale because new matter is continuously created to maintain the constant density as the universe expands. This continuous creation of matter ensures that the overall structure of the universe remains unchanged, thus adhering to the philosophical principle of an eternal and unchanging cosmos. Unlike the Big Bang theory, which is a singular moment of creation, the steady state theory avoids the implication of a beginning, proposing instead the universe is always existed and continue to exist in the same state. Rigvedic cosmology approaches the idea of expansion differently, emphasizing the cyclic nature of the universe. According to the Vedic thought, the universe does not expand linearly but undergoes cycles of creation, shrishti, and dissolution, pralay. In this model, the universe is created, expands, and eventually contracts back into singularity, only to be made anew in the next cosmic cycle. The cyclical cosmological reflection reflects modern scientific theories such as oscillating universe model, which suggests that the universe could eventually reverse its expansion, leading to a big crunch, followed by a new expansion phase. Therefore, Rigvedic understanding of expansion integrates with the concept of infinite cosmic cycles, contrasting with the more linear and progressive model proposed by Big Bang and steady state theories. Lastly, we discuss the concept of cyclicity. Cyclicity is the core concept in Rigvedic cosmology, where universe is viewed as undergoing endless cycles of creation, preservation, and destruction. The idea is captured by the concept of pralay, where the universe dissolves only to be created again, suggesting that time is not linear but cyclical. Such a view anticipates modern cosmological discussion on the oscillating universe or the cyclical model, where the universe experiences repeated phases of expansion, Big Bang, or contraction, that is Big Crunch. The idea of cyclicity also introduces a philosophical element to cosmology, emphasizing the transient nature of universe and the eternal recurrence of cosmic process. The Big Bang theory, in contrast, provides a linear model of time and expansion where the universe is definitely beginning and may have an eventual end. The fate of the universe, according to the current model, could result in continuous expansion, a big crunch, or a big rip. While some variations of the Big Bang theory incorporate cyclical elements such as Big Bounce model, the mainstay theory remains focused on one time event of creation and expansion. The steady state theory rejects cyclicity and linear progression. It posits an eternal, unchanging universe with no beginning and end, starkly contrasting the Big Bang in the Rigvedic model. The continuous creation of matter ensures that the universe maintains its steady state without any cyclic phases or endpoints. Now let us synthesize everything we have discussed so far. Rigvedic cosmology offers a profound and encompassing perspective on the universe's origin and that transcends modern scientific discourse. While the Big Bang theory and the steady state theory provide valuable frameworks for understanding the universe's evolution, they are largely rooted in materialistic perspectives focusing on empirical observation and physical processes. Rigvedic cosmology, by contrast, integrates metaphysical dimension that invites reflection on consciousness, time, and cosmic principles beyond the materialistic world. One of the primary ways Rigvedic cosmology offers a broader understanding is through its cyclical concept of the universe. Modern cosmology has recently begun exploring models such as oscillating universe, which posits that the universe could undergo cycles of expansion and contraction. However, this idea has long been central to Vedic thoughts, where the creation, srishti, and dissolution, pralay, are recurrent processes governed by cosmic principles like ratha, the cosmic order. The cyclic framework extends the modern discussion of cosmic evolution, suggesting that the universe is not a one-time occurrence but part of an eternal process. Scholars like David Frawley argue that cyclic view aligns with the certain modern cosmological hypotheses, including Big Bounce model, which proposes the universe may collapse and expand again. Additionally, Rigvedic cosmology incorporates the philosophical inquiry into the nature of time and space. In the Big Bang theory, time and space emerge from singularity, but the theory does not explain their origin or what may have existed. In contrast, Vedic thought process does not limit time to a linear progression, rather, it views it as cyclical, with infinite Brahma days and nights representing cosmic cycle of creation and dissolution. The understanding of time is more expansive than the linear view of often adopted by modern physics and allows for a more holistic exploration of the universe's continuous evolution. The convergence between Rigvedic cosmology and modern science also extend to the role of consciousness in shaping reality. In quantum physics, the observer's effect raises question about how consciousness interacts with the physical universe. Rigvedic cosmology, particularly thought through the concept of Brahman, suggests that consciousness is not merely a byproduct of material process, but is a fundamental aspect of the universe. Brahman represents both the immanent and the transcendent reality that underlies all creation, implying that consciousness and the material world are interconnected aspects of the same cosmic reality. This resonates with ongoing scientific debates in quantum mechanics, where consciousness is increasingly considered an essential element in understanding universe's behavior at subatomic level. Thus, Rigvedic cosmology presents a more integrated view of the universe's origin, encompassing physical, metaphysical, and spiritual dimension. It suggests that modern cosmological theories, while advanced, are only beginning to catch up with the profound insights embedded in the ancient Vedic texts. By considering the universe's cyclical nature, the philosophical inquiry into time and space, and the centrality of consciousness, Rigvedic cosmology provides a more comprehensive framework for understanding the cosmos. The synthesis calls for an interdisciplinary approach, bridging the gap between ancient wisdom and modern science to explore the mysteries of existence more fully. Namaste.